Hello friends, welcome to New Lessons. Today we will discuss about the second part which we have left about the mass and steady flow. And in the last video we have discussed about the nozzle and diffusers and some problems regarding that. Today we will start with some more devices, thermodynamic devices like the throttling device. Now it has an adjustable valve. The fluid flowing through this tube experiences a pressure drop. Means consider a fluid flowing through one exit porous plug. The fluid experiences a pressure drop as it flows through this plug. No net work is done by the fluid. Assume that the process is adiabatic and the kinetic and the potential energies are neglected. So by the conservation of mass and energy, both of them equating together, we get mi dot equals to me dot, that is the mass inlet equals to mass outlet, and it can be represented as, we have learned this in the previous video. If you go through the previous video you will not face any problem in this part. Q net plus m1 into h1 plus v1 square by 2 plus gz, this is the total work done. Net heat change plus q net equals to work done equals to w net plus work done. So in this case what happens, the main thing what happens is h1 is equals to h2. That means the pipe is kept at the same level, that means h1 is equals to h2, and the formula rather becomes, in this process is called throttling process. So what happens when an ideal gas is throttled, h1 is equals h1, that is the, in this case it is the enthalpy, input equals to output enthalpy. So if you consider CPdT, that is equals to 0, or the temperature, there is no net change in the temperature. So when throttling of an ideal gas takes place, the temperature does not change, that is delta equals to 0. We will see later in this other chapters. So first of all, a throttling device may be used to determine the enthalpy of saturated steam. The steam is throttled from the pressure in the pipe to ambient pressure in the calorimeter. The pressure drop is sufficient to superheat the steam. Now it is an example. You can see one way to determine the quality of the saturated steam is to throttle the steam to a low pressure, that it exists as a superheated vapor. Saturated steam at 0.4 megapascal is throttled to 0.1 megapascal, 100 degrees centigrade. Now if we determine the quality of the steam is equals to 0.4 megapascal. So in this case the control volume is this throttle. It is made to pass through a porous plug, and we'll get the relations from the steam table. The process is steady state, steady flow, no work, no heat, neglecting kinetic and potential energy, and one entrance and one exit. So by conservation of mass we get the formulas like this. Now according to the sketched volume, if you consider the mass crosses the control volume, neglect the kinetic and potential, we'll get these values as like this. All the values are 0, kinetic and potential energy. So the enthalpies of input and enthalpies of output is same. Now by considering the previous knowledge of what you have learned in the properties of pure substance, that is how to study the steam table, how to get the values of enthalpy, entropy and other things from the steam table, that will help you a lot in this chapter. So better to go through those videos previously before reading this. So h1 is equals to h2, this enthalpy remains constant, and hence it is equals to hf plus x1 hfg at pressure equals to 0.4 megapascal. So this factor, quality factor, comes out to be 0.971. So this was a small numerical describing what is throttling process and how it occurs and what are the characteristics of this throttling process. Next, coming to the mixing chambers. In case of mixing chambers, generally the hot air and cold air made to flow from both the ends. It is generally basically a mixing of two fluids occurring frequently in engineering applications. Now in this case there is a small numerical. You go through this numericals. These are very easy, very simple. Just it will build a concept and you will be well acquainted with these things. So in this case the control volume, you read these questions. In this case I will just describe the solution. The control volume is the mixing chamber. The property relation will come from the steam tables. Assume steady flow, adiabatic mixing with no work. So conservation principle. The steam 1 and cold water 2 is the input and saturated water 3 is the output. So in this case we have masses m1 and m2 as input and m3 is output. So m2 equals to m3 minus m1. Putting the values of conservation of energy also, if we put the values here, this is the conservation of energy formula, and if you will substitute in the next part, you will get, according to the control volume, mass crosses the control surface. We neglect the kinetic and potential energies, and note that the process is adiabatic with no work done. We have two entrances and one exit. So m1h1 plus m2h2 equals to mh3, m3h3. By substituting the values, by rearranging them, we get these values. Now from the steam table we get T1, P1 and H1 respectively. Now the things become simpler when we have all the values, we have the concept, we have the formula, just substitute them and get the answer. So m2 equals to m3 minus m1, it comes out to be 17.18. So I regularly tell you to go through the book, to go through as many as examples as possible. These examples are very important in building the concepts. Now another type of device, that is the heat exchanger. Heat exchangers are normally well insulated devices that allow heat exchange between hot and cold fluids without mixing the fluids. This is the main thing, that is these fluids are not mixed with each other. They are well insulated, but there is some change of heat between them, like the pumps, fans, blowers, causing the fluids to flow from the control surface. You can go through this diagram. Fluid bleed 70 degree centigrade is given. There is a change of heat in the middle part, and 35 degree heat is exerted because there is some change in heat. Now one more example regarding the heat exchanger. Air is heated in a heat exchanger by hot water. The water enters the heat exchanger at 45 degree centigrade and experiences 20 degree drop in the temperature. So the question goes like this: as the air passes through the heat exchanger, its temperature is increased by 25 degree. You have to determine the ratio of the mass flow rate of the air to the mass flow rate of the water. So the diagram will explains how to solve the problem. In this case, the control volume is the device, that is the heat exchanger. The properties are the ideal gas properties and the water steam tables. The process is considered as the adiabatic process and steady flow. And we have two conservations, that is the conservation of mass and conservation of energy. For two entrants, two exits, the conservation of mass will be m1, m air1, mw1 equals to m air2 plus mw2. This is a device in which we have two entrants and two exits. Now for two fluid streams that exchange energy but do not mix, it is better to conserve the mass for the fluid stream separately. That means m air1 equals to m air2 equals to m air, and mw1 equals to mw2 equals to mw. We are separating these two things, that is the mass and that of the weight of the air. Now similarly, progressing with the conservation of energy, we get the energy values as shown in this diagram, in this derivation. These are very simple derivations. Now using the incompressible fluid approach for this water table, Cp at weight is given. So we get m air by mw equals to Cp into del T, and mw equals to Cp air into del T. So we get 3.33 as the ratio of m air by mw. Now for the second solution, this problem is obtained by determining the heat transfer rate from the hot water and noting that this is the heat transfer rate to the air. Now consider each fluid separately for steady flow, one entrance and one exit, and neglecting the kinetic and potential energies. The first law of conservation of energy equations become E input equals to E output. So for the air case we have m air, mass of air into h enthalpy of air, plus Q. Similarly that of the water. And Q input air equals to Q output water. So in that way we can solve those problems. Here is one more thing to discuss about a pipe or a simple pipe that is considered as a control surface and the fluid flows through it. So in a simple power steam plant, steam flows through a boiler at 3 megapascal 300 degree and enters the turbine at 2 megapascal and 500 degree centigrade. So determine the inline heat transfer from the steam per kg mass flowing in the pipe between the boiler and the turbine. So you can see from the first part, the steam from the boiler is entered through the part 1 and it is exerted from the steam to the turbine. Now in this case, the control volume is this pipe section. The property will use from the steam table because the temperatures and pressures corresponding to them are given. Let me tell you, the flow of fluids through these pipe centers is often steady state or steady flow processes, and we generally neglect the kinetic and potential energies in this case. But in this case, the condition is so, or the flow situation is so as such, the work and heat transfer may be zero or may not be zero. So conservation principles, we have two conservation, that is conservation of mass, conservation of energy. We have studied all this before. Just get the concept, how many input, how many output, what to use, how the conservation of mass and energy changes as shown in the slide, and just put the values. You will get the values from the steam table. I have shown you about how to get the values from steam table. So once your concepts are clear, you can deal with any type of problem in any chapter. It may not be the chapter belonging to what you are studying. In thermodynamics, it's a mixture of many chapters and ultimately will get the better results. Now there is another example. You please go through this example. Air at 100 degrees centigrade, 0.15 megapascal, flowing at a speed of 40 meter per second, and it flows through a converging duct with a mass flow rate of 0.2 kg per second. The air leaves the duct at 0.1 megapascal at speed is 113.6 meter per second. So in this case, the exit to inlet duct ratio is 0.5, that is given, and find the required rate of heat transfer to the air when no work is done by the air. Now we draw the diagram as such. It is given that in the last line, the exit to inlet duct ratio is 0.5, means they both are not equal. They are at a ratio of 1/2. So similarly, we have the control volume as a duct, converging duct in this case, because the ratio is given as 0.5, it is decreasing. The process is steady flow. The property relationship, we assume it is an ideal gas and we use the ideal gas relations. Now coming to the main point, that is the conservation of principles. We have two types, that is the conservation of mass and conservation of energy. One entrance, one exit, but the diameter is changing. So we consider it can be as a diffuser type. So by putting all the formulas, this is the net equation for the conservation of energy. Now combining these two equations, we will get these results. This is just nothing but solving. This slide seems to be very clumsy with lots of numerical formulas and values, but these are very simple because we have read everything beforehand, and this derivation of these certain formulas, applying them, and we have solved in previous simple numericals. This is just an example of a complex numerical. It can be as long. Now we'll get the values of T2. You please go through this, you will understand. The analysis of your views will be different from mine, obviously, and the way you will understand it, nobody can explain you. This is better way to analyze them after you get all the concepts. So in this way we can solve many of these problems regarding the steady flow and mass flow equations. In the next session we will study some more things about the thermodynamics. Hope you like it. Thank you.